My name is Joseph T. Wunderlich. I'm a professor of engineering, architecture, and computer science. This is an introduction to machine intelligence, an update of something I've made a decade ago. I've been involved with machine intelligence for 35 years. I have a couple of neural network chips, 1991, 92. One showed up in the patent office, other as part of my master's and PhD research before I did IBM research on supercomputers. So this is recently 2025, the NVIDIA GPU Technology Conference, where Jensen Huang, CEO of NVIDIA, the most important neural network hardware provider right now in the world. We have trade restrictions on it, and there's all kinds of lectures that I'm putting together and others just on that. So what he shows now the history of where we've come from in the beginning from the of neural network type AI. There's other kinds of symbolic AI I'll talk about in a second historically, but the neural network type AI, a perception type of AI with, for example, speech recognition, and then generative AI where we're generating images and other media, and then the agency where we're talking about right now reasoning models, which are more sophisticated, take more time to train, need much more computing hardware power. And then where we're headed, where the physical robots, the physical AI in the robots, in the autonomous vehicles, the planes, the cars, the underwater vehicles, autonomous machines with sophisticated sensory fusion, processing, awareness of physical realities of the world and making decisions based on that in real time. And then you see the scaling of that here he has here based on each of these above here, with pre-training being most important with the data, and then post-training. So you have the training of your data, then you train the model, you create the model through training. There'll be weights in the neural network after training. And then there's an inference phase where you're implementing it, just using it. And so he's showing how that scales differently over time as we progress. So here I'm going to talk about first the two different types of AI. Until recently, neural networks were considered something different than symbolic AI. Well, I say recently, past decade or so or more. Deep learning neural networks is synonymous with that. But there is another type of AI, the traditional AI, which is code using knowledge bases, programmed heuristics, predicate calculus with rules and coded inference, and something similar to probabilities called confidences. And so that is one type of AI. It's still around. And then what we're used to now is neural networks, deep learning type neural networks. And they were called generalizers. So the idea is you train this thing with a set of data, but then you can present to it some other data that's similar but different. So it essentially interpolates, extrapolates, generalizes during the learning when it's being trained. And then there's weights. So the weights we're going to see are the interconnection weights, and they lend themselves to linear algebra, matrix manipulation, vector register kinds of architectures that I teach in other courses. It's not in this introduction. And then once it's been trained, it will respond very quickly to anything in the training set, of course, without having to learn the training set again, but also anything that's just similar, a little bit similar, new stimulus will result in desired outputs that you would expect, even though it hasn't been trained on it, because it's learned, the model has learned a certain behavior. Okay, so then we have a couple problems here. I'm just going to skim over it here, but you need to kind of read through it. So first we have a non-AI example where a husband and wife are deciding whether or not to get a puppy or a kitten. And they've also an assumption here that if either one of them really wants the kitten or the puppy, then they're just going to do it. So they yield to their partner. So that means, well, if one wants one, you're going to get it. And if both want the kitten, you're going to get it. Otherwise, you'll get a puppy if neither one of them really wants a kitten. And then there's this standard logic that you would put in your algorithm for that. Then the symbolic AI, what we're going to do is have confidence. Is like the parents only, you know, have a certain degree of confidence in their decision process. So where they were saying, yeah, definitely I want it, well, now it's only 80%. Or I don't think I do, then that's 20%. So you put those in, and then I have a link here to an expert system I wrote in 1991, picking a toy for a child, where you can see the predicate calculus and learning the confidence values that go into that kind of thing. And then now a neural network. So case in number 1 here, this is the first neural network, and we're using not the fuzzy data here, but the very first just straight logic from above here, and we're going to train the neural network to do that. And then there's the steps of going through that. You initialize your weights randomly, typically, although there are methods certainly for doing something other than random to create faster learning. And then you go through a training set. So each one of these are exemplars. So you have inputs and output exemplars, and you present the inputs and look at the output. And if it's not the desired, so it won't be the desired first because it's going through these weights here and the way, and these neurons. I'm not explaining the algorithm here, that's later on, but these neurons are firing with some kind of signal, and it's an analog signal. It's not just binary coming out of this. So what will happen is you're hoping for some kind of binary output, but you're going to drive towards that with your analog values based on feeding each of these exemplars through one at a time, and then comparing what it actually puts out, starting out with randomized weights, to what you want, generate an error, back propagate that, and change these weights incrementally. And you do that over and over and over again through all the training set. Each presentation of the training set and a back propagation changing of weights is 1 epoch. So here's a number of epochs for essentially an OR gate. Then we have a case down here where we're going to use the fuzzy, if you will, somewhat preconditioned data borrowed from the symbolic AI case up here, kind of fuzzy data going in, and then see what happens there, and it still learns, showing the resilience, the robustness of the neural network.
So now continuing this same example, if instead of case number 2, instead of randomizing the weights in the beginning, we use the weights that we learned in case number 1 with just binary inputs and outputs, no fuzziness in the inputs, we see that then it learns much faster. Then case number 3 is just as I think we mentioned, if once it's learned, it will just respond to an exemplar almost instantaneously. Case number 4, the same thing, almost instantaneous response if you give it something that's not exactly the inputs, something a little fuzzier in just the feed-forward suite. It doesn't need to learn anymore, just responding. Now, case number 5 is an odd case where it's not really odd. I mean, this happens all the time where the things that are being asked to be done, learned in the training set, and the exemplars are contradicting themselves a little bit. So if for this case of picking a puppy, if for some reason the one parent wants a kitten, or only one of them wants it, then the other one just is oppositional and says I don't want it, and if they both agree, then that's not they're not going to get a kitten. So I might have misspoke here. If they both want to get, if either one of them wants to get a kitten, they get a kitten. If they both want one, then they end up getting a puppy, which so the logic's a little bit messed up here, but there's it's human behavior, so you don't want to try to make it work out too much. And the neural network's actually pretty good at reading into this the intent and trying to resolve something. So regardless, here you have this what's called an exclusive OR, and it's counterintuitive because to even have such a thing, if you think about the stimulus, if both are 0, we get a 0 coming out. If you just imagine these signals going in and a signal coming out. And then you have 0, 1. Well, you're giving a little bit of juice, right? A little bit of 1, a little bit of, this, some value of number magnitude. So you're going to get some magnitude coming out. If the other variable, if x is 1 and y is 0, then you get something coming out. But if you have both of them feeding in, you get a 0. Well, now that's not going to be easily solved with just a single neuron. That actually held up research in neural networks for a bunch of years when some renowned MIT researchers, Minsky and Perret, said you can't do these nonlinear separable problems with a single perceptron. So it took almost 16 years before Rummelhart came up with backpropagation and layered networks to solve this type of problem. So anyway, here you can see now that in the graph it took longer to learn, almost 1,400 epochs as compared to 200 to 600-ish in the other previous examples, because this is a nonlinearly separable problem. Now this case number 6 is a little bit more odd, where for some strange reason the parents only get a puppy if both of them plus the neighbor all either agree to get a puppy, or for some really odd reason all want a kitten. So, stretching the logic here a little bit, although you can imagine the part where if the neighbor doesn't want a dog and the dog's barking, you could factor that in somehow. But overall the logic's a little weird, but just allow it so we can get this problem defined. And in reality, there's all kinds of problems, real world problems, that lead to this kind of data. So you have now 3 variables, input variables, mom, dad, and the neighbor. And so you have 2 to the 3 equals 8 exemplars when you have, how many permutations of 3 binary variables you have. You have, if you have n number of variables, you have 2 to the n permutations. So you have 8 different combinations. And so this is the data you're looking at here. So it's almost like a big giant exclusive OR if you think about it, where the first one and the last ones are the ones contradicting the most, the biggest contradictions between the number 1 and 8. How long does that take to learn? And so you see that up there, and over 1,000 epochs for that to learn. Now I'd like you to take some time and read through this, the steps of the algorithm development, 1 through 8, and then look at some code. So take your time and look at this. This was code I wrote originally not in MATLAB in 1991 to just lead up to tweaking the neuron transfer function to allow parallel processing in hardware to make single chip neurocomputer. That was my master's thesis. And then a second processor, I made a whole different kind of theory with more of biological inspiration after that. So I made 2 neural processor designs in 91 and 93. So take a look at this, look through it. Most of you know how to program, so just look through. You look at this stopping tolerance, ask yourself how that works, and the learning rate. That's something that you'll learn about. You can read other lectures. You don't want that too big, or you're not going to, it's not going to learn. And then you'll see the weights being initialized and just random values here. And then the main code. Go down, take a look at it, see if you can figure out how these incremental changes are being made to the weights. And then the output plotting here at the end with some metrics, and then the whole code section for the 331 bigger architecture. And that's all the same, except just scaled up a little bit. And so just look through that, make sure that all makes sense to you. And lastly, this larger scaled up one, ending and outputting some metrics. So now some explanation of the above code, a little more detail from a lecture on this. Firstly, we don't want to worry about CPU time anymore. This is something we used to do 20, 30 years ago. But now, because of the way computing is distributed and there's multiple cores, levels of caches, shared memory, you don't know exactly how long a particular machine instruction is going to execute, so you can't really do this, use this kind of metric in a useful way. If you want to see more on that, you can click on the syllabus to my advanced computer engineering class where we talk about those kind of things. It's a parallel processing class. And then we have a selection of whether it's which architecture, 221 or 32 or 331. So 2 inputs, 2 hidden, 1 output, or 3 input, 3 hidden, 1 output. Then I just point out here next that it's a command line interpreter, which I already mentioned. And then the learning rate. So if you want to learn more about that, you have to look at my more advanced lectures and talk about that. But in general, you don't want it too large, especially for nonlinearly separable problems where the weights need to slowly change. If you have too big of a learning rate, you will miss the local minima, jumping back and forth on the error surface over a trench that could lead to one. And then we have epoch count of 2000, so you don't want to go too high, or just don't let the thing go forever if it's not learning, especially if you didn't pick the right learning rate. Then we have stopping tolerance, which this is an analog system. This is an spitting out pretty high precision numbers between 0 and 1. And then we're driving it towards asymptotes of 0, 1. And so what we see here now is one of the cases being picked in so this is the input section where I'm defining essentially what case that I'm evaluating here. And this is case number 2 if you look at the inputs there and the desired output. In MATLAB form, MATLAB has vectors and matrices, so this is a matrix with vectors that you see there. And then you see below reference to it learning. So now we see in a while loop here for as long as all 4 exemplars, all 4 of them have not yet reached within a stopping tolerance of the asymptotes of 0 or 1 that we've defined a stopping tolerance above. Then you keep learning, and then for I equals 1 to 4, you see below there, that's for all 4 exemplars in this particular training set. We want to evaluate the outputs of C, D, and E neurons, not A and B, because A and B are just splitters. And then we use this 1 over 1 plus E to the sum of the weighted weights times the inputs for each of these neurons. And that is the a transcendental function, a sigmoid. This is sigmoid. It needs to be continuously differentiable for traditional neural network learning that you can learn about in other courses with me. Now in this case, we're going to take a look at using weights from a previous training and using them to speed up learning in a new situation. So we're taking the weights learned from case number 1, the first neural network training, where the inputs were purely binary, and we take those learned weights and we're going to use them in case number 3, where we have fuzzy input, the same fuzzy input from case number 2, where you can see that the learning took approximately or a little bit over 500 epochs to learn. And now with these improved weights, or weights from a similar situation, it's the same kind of problem, it's just fuzzy inputs, and we see that the neural network learns 225 epochs. So you see in the code below, beginning at the top of the screen, where the initial weights are simply randomized. That's what you typically do in most cases. However, even though there are mathematical methods to optimize those, And then this particular example, we are overwriting those initial randomized weights with these weights from a previous training. And now we can take a look at the actual learning going on here, where the change or the back propagation is going on, and it's going firstly through the JK weights, which are between the hidden layer and the output layer. So we're taking an error signal defined by the difference between what we're actually getting out of the network as we're learning and what we desire, for all these exemplars, in a least means squared error gradient descent way that you learn in other courses with me. And so you can see in the slide here that we're changing these weights, and there's two sections. This first part is in the JK weights, and then we back propagate. Now, it's not completely clear why it's the way it is in this algorithm, and it's different than in the JK level unless you look a little further into the calculus of it all. And so, and derive these equations, why they actually look like they do. But essentially, you have to go through the neurons, to get to the layer that's closest to the beginning of the network. You've got to propagate the error through the weights and the neurons in the hidden layer, and the weights between the hidden and output layer, and all through the neurons in the hidden layer, to then change the the weights, change the weights in the IJ layer between the input and hidden layer. And there's a link to see more about that below if you like. So this is a big neural network conference with 300 papers submitted, and I got an award for comparing top-down and bottom-up. And then by top-down, I mean mathematical models versus bottom-up is for biological models. And so I have a couple chips that I designed in 1991 and 1992 and 3 that you can see there. It's also a draft book chapter.
And finally, here we have some linear algebra representing the matrix of weights times an input vector, and then how that's calculated in the dot product. And then each one of these will be the weighted sum. They multiply, accumulate into a neuron transfer function. And you can click on this link here to see some details of basic linear algebra if you're not familiar with that.